is a problem where two items are moving or there's some movement in relation to another item and we have to figure some things out around that. Okay. We gave you the sliding ladder problem yesterday, right? On the board in the shop. That's like the most famous related rates problem there is. Yeah, it's the sliding ladder problem. It's always example one. So I didn't put it in there in your packet. I did put that together this morning, just a last minute thought, so if there's a mistake, we'll just deal with it.
Example 2 is the sliding.
Okay, so here's another popular one. Example 1. It has to do with spheres, so we can do, most of the time, we're looking at triangles, spheres, circles, maybe a rectangular prism, shapes of that nature that we have. Surface area, volume, area, perimeter. Okay. Air is being pumped into a spherical balloon at a rate of 5 cubic centimeters per minute. Determine the rate at which the radius of the balloon is increasing and the diameter of the balloon is 20 centimeters. So, the first thing that I recommend that people do is annotate. You identify the important information. Okay. So what's important here? 5 cubic centimeters. Okay. Using the units, is that a length or an area or a volume?
Volume.
Yeah, it's a volume, right? And so you can automatically know that's a volume rate. So we will probably, so you don't have to write this down, but we will probably have a dV/dt in there, right? Volume is changing with respect to time, right?
Yep.
What else is in there?
20 centimeters.
And what is that?
Diameter, so you really get 10.
Okay, what's the radius then, if you're thinking that way? You said it, so I showed. Okay, there's one more piece of information you want to think.
Increasing.
Okay, the rate at which the radius is increasing, right? That would be, it's a rate, so how would you note that? Right, the derivative of the radius with respect to time. So you're just identifying stuff, right? You drew a picture already, I trust?
Yes.
Of a sphere, and it's a perfect sphere.
Yeah.
With R10.
That's how you draw a sphere.
Yeah, that's how you draw a sphere.
It gives the impression of a three-dimensional. What's the formula here?
So D.
Volume.
Yes.
V equals. Here's the third.
Third times.
4/3 pi r cubed.
So first is pi times 10 cubed.
Not yet. So, yesterday in the sliding ladder problem, we had the ladder. Did the ladder ever change size?
Nope.
So we could put that in right away, correct? Okay. Do both of these change size?
Yes.
Yeah, so we can't touch them yet.
Okay.
Okay, we need to leave them alone because they will change size when things are expanding, right? Okay, so what's changing?
The radius.
The volume.
Yeah, so you got, I mean, it's right there, and you've already identified it, so. We have those values. Oh, I just crossed it out, didn't I?
Yep.
Okay, do we know the radius? Determine the rate at which the radius, so that is gonna be our,
unknown. So that's what we're trying to find.
yeah, that'll be what we're trying to find. And then, at the moment, what is V and what is R?
We can plug in volumes.
R is 10. What's the volume?
3 plus pi over 2.
Yeah. Let's think you 1,000.
Yeah.
Yeah.
So 4,000 pi over 3. Okay. We are not going to need that number, but it's there.
Great.
Okay, you'll see why we won't need it. All right. Setup, correct?
Yes.
Any questions?
No.
Okay, Kylie understands. Anybody else? Good. Okay, your last step is, I actually added this. You've been piachenga'd.
Okay.
Piachenga'd.
Yeah, change.
You have to calculate the derivative once everything's set up, right? So, with respect to time, calculate the derivative of that. So what's the derivative of v?
5.
1. It's just, it's 1v, right?
Yeah.
So the derivative of v is 1 dv dt. And it's implicit because we're with respect to t. Yes, it is. We will plug 5 in there. You always want to be very deliberate because you're going to earn a point for writing that down, writing this down. Okay? You're going to be very deliberate about that. What's the derivative of the right side?
Oh, goodness.
12 over 3.
Yeah. 12 over 3, which is
4.
pi. And then r squared is power rule. Power rule.
Yep.
And what else?
Does that equal 5?
We're not done yet.
What do you mean?
Implicit, so what do we have to add? dr, dt. Okay, everything that, every time we derive it in related rates, we have to add that something d over dt.
How would you know that it's
This is always with respect to time in a rate problem. Remember we talked about,
how did you know to add the dr over dt?
because I differentiated r.
You did it?
I differentiated r. So derivative r with respect to t. It's a rate's always time, like miles per hour, feet per second. There's always a time component in it, so we always put dt. All right. Now it's an algebra problem. We can plug in 5, like you said, and what else? And we know r, right? And in the end, hopefully we see that there's only one variable left.
That's the problem. You're a 5 or an S?
That's 5.
There's a crooked part, there's a corner that's not differentiable right there. Okay.
I'm blind.
What would you rather be, blind, deaf, or dumb?
All?
Okay.
So I get like, everything taken care of for you.
Yeah, but there's also something that you're missing in life there that people value very highly. It's called freedom.
That's true.
Yeah.
It's called vision.
I mean, half the world doesn't do that anyway, so.
But there you are.
Is that it? We don't have to.
No, so again, If that's a multiple choice answer, you're probably gonna either have that as an option, or it's gonna be a calculator friendly and you're gonna put it in the calculator. And if it's a free response question, you just leave it. Okay?
So that's the answer at that point?
Yep.
Yep. Okay. So, spherical volume. Follow the process. Okay, next. Okay, the ladder, I actually put a ladder
Yeah,
problem on
you
here.
did.
We're not gonna do it,
Okay.
but you have hopefully wrote some notes down.
Yeah.
Okay. All right, let's move to, there's a good one.
Okay, number 5.
Number 5. I did not write, we have changed it on your paper for you.
Yeah, change.
Because it goes to the speaker.
You guys are watching, you want to just take notes?
No,
and do
it
it?
would be negative 10. Just think how it works.
Or you could
Goes on that here. So it would be negative 10. Cosine is cosine, cosine is negative 1. See what I mean? We just need to be able to square x and think it's negative 10.
Good? Okay, can you draw, let's read it. A rocket is launched on a vertical trajectory and is tracked by a radar station that is 3 kilometers from the launch pad. The vertical speed of the rocket at the instant when the distance from the rocket to the radar station is 5 kilometers, and that distance is increasing at 5,000 kilometers an hour. Can you draw a picture? Okay, how about it? What's, so anybody, oh, and annotate. We can do that too.
So the way I see it here,
So the truck.
can, secant, turn becomes negative 10.
Got some important mathematical stuff.
And then negative 10.
That's,
You don't have to get too cutesy.
How's it a triangle?
how is it not a triangle?
Because you're comparing it to the,
From the station?
Okay,
What is the best triangle? I would draw my entire life.
Spider-Man.
I think best
Okay, so radar, rockets launched vertically. What are our distances?
How do you know it's to the, does it matter if it's facing the left or the
We're
right?
3 kilometers from the launch pad, so here's your launch pad. Distance from the rocket to the radar station is 5 kilometers. That is something that people, that is direct distance. And then the rocket is,
4 kilometers.
okay, and this distance here is increasing at 5,000 kilometers an hour. Okay. So you have to interpret those numbers correctly. It's got a super rangefinder.
So, Mr.
What?
So if it's 5,000 kilometers away right now, that means that an hour since launch. Oh, 5, never mind.
Not necessarily. Okay.
I
Alrighty, good. What formula are we going to use? Yeah. Got that? Right, because the 3 legs of the triangle we're messing up. And then always, see there are 3 variables, right? We only want 2. Is there a variable that we can get rid of right now?
No.
Z is Z changing. As the rocket goes up, it is 3.
Yeah, that's 3. X.
Yep, that never changes. Pretty sure that radar station's not gonna get up and walk away.
I would hope not.
Unless
That'd be
it's
weird.
like controlled by the Empire or something, so. Imperial walkers. So, yeah, we can put 3 in because this never changes.
We have to find why.
All right. What's changing? What's left over? Which of those do we have?
We've
And
that's what we're on.
yep, that's probably it. Okay. And Y is and Z is. Somebody recognize this as a 3, 4, 5?
Yep.
This is what's in it. Okay.
Elise, you with us?
Wow, Caleb.
All right, so we are set up. What's last? Piachenga. Okay. What's the derivative? Okay, that's a constant, so what can we do with it? What's the derivative? 0. Right, so the derivative of this is 0.
Yep.
Okay, so that is 2y
Equals 2Z. No.
dy.
Yep, I got that.
Okay, yep. Okay. And then 2z with respect to time.
Not with the
And then plug and chug.
2. Right.
Now you have an algebra problem.
Because we know Z, right?
Yeah, we know y is 4. And we know z is 5. Good to go. Cool. We know dz dt as well. So notice that we didn't even have to worry about x,
Because it just took away.
which is kind of nice because nothing's changing there, so we don't worry about that variable. So dy dt is 2 times 5 times 5,000.
Great.
So you just,
Free response answer.
so you wouldn't want to simplify it to 8 and 10?
You can. It would not be any more correct than that.
The one day wrong, but it gives you more chance for error.
That is true.
And what are the units?
Hours?
Yeah, it's a rate, so it has to be, use the distance, kilometers, and the time factor, hours. You could simplify that if you really want to.
If you're doing a calculator, then you
No, this would be a no calculator problem for sure.
Yeah, that was pretty easy.
Pretty straightforward. Whole numbers, 3, 4, 5 triangles, all that stuff. Right. We good? Or we not good?
Who's good?
Where'd you get y equals 4?
Because it's 3, 4, 5.
So we're in the Pythagorean theorem, right? So 3 squared plus y squared equals 5 squared. Solved.
I'm going to solve it.
Okay, let's see here. Oh, we'll do one of the circle ones.
Okay.
Exactly 70. Area of the circle increases at a rate of 1 centimeter squared per second. Oop, I didn't catch that of it. How fast is the radius changing? And the radius is 2 centimeters. So pictures are pretty easy, right?
Yep.
I dare you to draw a perfect circle.
I cannot.
It's physically
Impossible?
improbable is a better word.
What? Anything's possible.
What you have to consider is that there are an infinite number of points around a circle, and that every single one of those would have to be the perfectly same distance around the radius.
To get it perfect.
While it could be physically possible, it's pretty much impossible. Okay, anyways, what's the formula we're working with?
The area.
Yeah, area right there. You might take note that I do not give you any of the formulas we're working with,
Yeah, I see that.
but if it's basic like Pythagorean theorem, sine, cosine, tangent, perimeter area, I said that, didn't I? The sine, cosine, tangent, Pythagorean theorem, perimeter, and area are not going to be given to you. But if it's like a volume of a cone, we're going to give you that formula. Okay, so. Okay, what's changing? Radius and area, right? Area of a circle increases at 1 centimeter squared per second. We don't know the rate. And then at that moment, R is 2. We do 4 pi. I moved quick. You still following?
Yep.
Good. Okay. What's next?
Is that D and A?
DA.
What?
So the area increases at a rate of 1 centimeter
So
squared
the
per second.
area.
Area rate. Pia Chenga. Duh. You're gonna be an AP exam and you're like, duh.
Yeah.
Somebody's gonna do it and everybody's gonna laugh.
And then we're gonna get yelled
What's
at.
the derivative? What?
Yeah.
Why is A equal pi?
Because you plug 2 in to the area formula and get the calculate the area. Okay.
He's like,
Derivative, David? Area equals pi squared, so it,
what?
the entire derivative is 1. Okay, 1 what? Okay, equals
2R. And then you plug in for R.
Thank you, Kellen, for serving bacon. Don't forget your respect to time. Okay, so now continue. Plug R in.
Plug in 1 for D8.
Okay, D82 is 1. 2 pi
I heard it from her
R.
too. It wasn't his. What did he say? It was Porter.
Okay, divide 2 pi times 2.
Yeah.
Sorry, we're trying not to interfere, but it's not working. Can you read that?
Kind of.
1 equals 2 pi times 2. Radius is 2, the RDT.
Oh, okay, that makes sense.
Oh, heck. We're not gonna do the second one, so I might as well write it coherently.
Okay.
Mosher and
Do we just leave it?
I wouldn't worry about it. 1/4 pi. What are the units?
Centimeters squared.
Okay, is this, so area is centimeters squared.
Also,
Just
that's
be careful. Radius is only a length, so it's just centimeters. Okay,
Okay.
so lengths, singular, areas squared, volume is cubed.
Okay.
Helen Jansen.
is that 2 from the radius and volume?
This really is.
And it's not squared because we drew it identical.
Right. Hey, anybody notice anything funny about circle derivative, the area derivative?
It's why can't I think of what it's
I don't
right
know.
now? But I do it.
You know it, I know you know it.
Yeah.
It's a 2 pi sandwich.
No.
Say it, Hannah.
Say something.
That's the
Yeah,
circumference.
that's like, I couldn't think of the
The
name.
derivative of the area of the circle is the circumference.
There you go, Hannah.
Get out of 10.
Mary was thinking about it.
Guess what? The derivative of the volume of the sphere is
The area?
surface area. Did we do that one? right?
Why do we
That's
learn
enough.
it as a derivative?
Oh
That's
my
the surface area
goodness.
formula for a sphere.
Why do we?
It's kind of funky. I don't know why it works, but that's the way it is.
That's
Pi r
weird.
squared is surface area?
Yeah, that's the area, but.
Okay, let's do.
8.
Oh,
Moving towards him?
that's the same problem we've already done. I thought I put, okay. There are problems where I thought I put one in here just to give you an idea of what might be coming. The rocket launch problem. Right?
That's such a cute little.
You can change that just a little bit
Okay.
to involve the angle.
Is that still a
What formula would you use with that picture, Caleb?
Gosh, Caleb, pay attention.
So instead of what is the distance between the rocket and the station, you might be asked what is happening to the angle.
So
Of
would you use
elevation.
the sine, cosine, tangent?
Yeah, which one?
What is it in the next one of which you noticed?
So your formula
Opposite of
would change to a sine cosine tangent problem. Okay. So if you draw your picture, look at the variables and pick the formula that you might need to use. Okay, it's the same process. You just need to be aware that those are possibilities. Okay.
How do you?
We've already done like that. What?
Oh wait, no, that would be.
Or, yeah, let's talk about the derivative of this then.
Yeah.
Okay.
What
Here's the launch pad, right?
Yeah.
Let's say X is 5 kilometers. Is that going to ever change?
No.
No. So we're going to get rid of the variable, thankfully, right? What is the derivative of that? Derivative of tangent is? Somebody said it. Secant squared. Cotangent, cosecant. Cos go together.
And tangent is.
Don't forget your dt. And then the derivative of y is 1/5 dy dt. So Same process, again, just knowing your memorized derivatives.
Why did you use that? Why did y equal to 1?
Huh?
Why did y equal to
You
1?
derived y.
You would have
The derivative of y is 1.
you would have 5.
It's 1/5 y. Same thing, right? Okay. I'm just trying to give you a few little pointers here, kind of give you some guidance. I cannot show you every possible problem. I mean, it's just, I did one like that. We can cross that out. So this is a problem where you have a water trough.
That's a beautiful truck.
There's a little bit of water in there and it's leaking,
It's leaking?
a little puddle.
Yeah.
So this is a volume, surface area, perimeter. What kind of problem? Yeah, it's a volume problem. Prism volume is base area times height. What is the area, what shape is the base? Yeah, it's a triangle, so the volume is going to be 1/2 triangle base times triangle height times prism height. Okay, so, and again, you'll get to the point where there's only two variables. So, just work within what you have.
Is that one of
That's a,
Yeah, what is it, 1 over what?
it was supposed to be 1/2, so it doesn't look like it.
T? B over...
So base of the triangle, height of the triangle. Right, that's base area. Again, generating formulas, working in the
Is that
problem.
weird T at the bottom of anything?
It's a subscript height of the
It
triangle.
says like it's on
So when we have several variables flying around, sometimes we have a height of the triangle and the height of a prism.
So
If
then
we
they
wanted to
use
note the
subscript.
difference between the two, we would start using subscripts and that. Here's another. This is going to use similar triangles you've ever studied. So a light is on top of a 12. Okay, so we have a pole with a person walking away, and there's a light that's shining over that person. The person casts a shadow.
Okay.
Okay. Do you see the two different triangles?
Oh, yeah. Because there's the big one and then there's the small one.
Big triangle, small triangle. Okay. Some things that never change. The height of the person and the height of the pole, right?
Yep.
These change. Because the person's walking. Right, so as the person walks away, the shadow length's going to change, and so is the distance between the person and the pole.
That would be great if they took the shadow moved away from the pole from the person's.
Okay, how do I set up a problem, a formula for this? Here's one triangle, right?
Yeah.
Okay, so we're going to put 5.5 over y, height over length.
Yeah.
So the other one has to equal height over, what's the length?
X, Y.
X plus y. Okay. And you have your formula. So,
Okay.
considering similar triangles, and one of the things that is not studied as well as it used to be, because we don't have a traditional geometry course anymore, is similar triangles and congruent triangles. So, I'm gonna flip that one. Okay, here's a cone. I'll give you a hint on this one. You're going to use similar triangles here as well. So this is kind of the challenge problem because you have 3 variables and you have to eliminate one with a system of equations.
Find the derivative of each of these and multiply.
Eliminate a variable with so these problems can get really difficult. In the interest of time, we usually don't make them really difficult. This is about as hard as they get. Okay, so I think we're good. Any questions? No. Calvin, Janice?
The level of difficulty in like the ladder one and the spear one, or where did I get to?
It's not a hard problem. Okay. So, in putting these on a test, you have to consider, do they have enough time to complete it? So no, it's not a hard problem. Very straightforward. Are we good?
Yeah.
Okay. So, I think
I have a question that's a little off on this.
I'm going to change the practice a little bit. So finish the packet. Because my mind has been chewing on this, on how to do it better for 5 years, and I think kind of came up with something right this morning, right when the bell rang. So I built that sheet, and then it was like, oh, that's a good idea too. So I need to change. So the homework is usually from the book, but a lot of these problems I found are better. Okay, those of you that are just practicing, that'll be due Tuesday. Okay. Your test review day is Tuesday, and we have a test on Wednesday. Okay, so get your minds in your memory cards. Do the problems on the test review that I've posted if you're studying. Okay. And what else was I going to say? Record your memory cards. Some of you are doing a pretty good job of filling out that form that I posted on a weekly basis. There's about 5 of you that have done it since the first time.
Oh, every week.
What I said was any time that you have gone through your memory cards a couple times, just post it. It takes you a minute, right? So.
Yeah, I got it 0.